Hello, it's a pleasure to welcome you to this week's HoloTube talk given by Juan Hernandez. So Juan is a postdoc in Brussels, and he will talk about entanglement, entropy, entanglement and complexity in various holographic models. So the stage is yours.
Thank you, Martin. And let me begin by thanking the organizers for letting me present today. So as Martin just mentioned, my talk is about entanglement and complexity in various holographic models. And this is based on work with some people and also a work in progress in some other areas. So very quickly, I just want to mention that I will be talking a little bit about what entanglement and complexity in the island phase and how to interpret some leading contributions to these quantities in terms of entanglements and complexities of islands. And then I will proceed to a sort of second part of the talk in which I'll be talking about how some bounds on entanglement and complexity can actually provide some bounds on certain intrinsic gravity couplings in certain holographic models. So let me just begin by introducing the concept of entropy. So there's various important concepts of entropy. A very well-known one is entanglement entropy, which is a microscopic entropy. So if we imagine having some microscopic state phi in a quantum theory, we can find some reduced density matrix by tracing out the complement of a particular subset of degrees of freedom. And then we can find an entanglement entropy by computing the von Neumann entropy, or the trace of rho log rho of that density matrix. And this gives us the entanglement entropy of those degrees of freedom A. And this gives us a quantity that quantifies the amount of entanglement between those degrees of freedom and everything else. Another important concept of entropy is a more coarse-grained concept of the thermodynamic entropy. So if one has some type of coarse-grained description of a system, like a statistical or thermodynamic description, and we only keep track of certain observables and not the exact microscopic states in our system, then simply counting the number of states that are compatible with a certain set of observables and taking the logarithm of the number of states gives us a thermodynamic entropy. And for example, for black holes, the observables that one would have are things like the mass, charge, and angular momentum, and the thermodynamic entropy would be given by the area of the horizon. And very importantly, in a quantum theory, the entanglement entropy is actually lower bounded by the thermodynamic entropy. But why is entanglement entropy important or interesting? I would say that a lot of the motivation for studying these quantities, especially in holography, is from this model, this way of trying to relate entanglement and geometry. So there's this model that says that entanglement builds geometry, and this can be seen very sharply from the HRT formula for entanglement entropy in holography, which actually gives an equality between the entanglement entropy of some particular subregion of our boundary CFT and the area of some extremal surface, the HRT surface. There's a very clear connection between a geometric quantity, this area, and the entanglement entropy, an information theoretic quantity in the CFT. Moreover, it has been shown that by carefully studying properties of entanglement entropy, and in particular, there's something called the first law of entanglement entropy, which relates infinitesimal variations of a particular state, in which give an equality between the change in the entropy and the change of the expectation value of the modular Hamiltonian in that state. And it turns out that passing this first law through the holographic dictionary provided a way of actually showing that even the bulk Einstein equations have to be satisfied, at least at linear order. So this is an example in which even dynamics can be deduced from entanglement entropy, or rather information theoretic considerations. Another example is entanglement wedge reconstruction, in which it was shown that for a particular density matrix, so only for a subset of the information in a particular system, one can actually reconstruct a subregion of the holographic dual, namely the entanglement wedge of this boundary subregion. But of course, a few years ago, Susskind famously said that entanglement entropy is actually not enough. So if we want to do these type of considerations, they're very nice because they give a nice way of constraining gravity, geometry, and even gravitational dynamics from information theoretic quantities. But the issue is that entanglement entropy doesn't actually probe all the regions in a bulk holographic dual. So as an example, we can think of the thermal field double, in which we have some CFT on the left side and the right side. And if we take some particular subregions of both sides, so something that's both a part of the region on the left and part of the region on the right, and we take the entanglement entropy of that quantity, at t equals 0, if the region is large enough, the entanglement surface, so the HRT surface, actually goes through the wormhole in the middle, the Einstein-Rosen ridge. And as we evolve in time, it can actually probe slightly into the interior of the event horizon. Even the shallow interior of the black hole can actually be, in a way, reconstructed from these information theoretic considerations that I've been mentioning. But the issue is that entanglement entropy thermalizes relatively fast. And what happens is that as the surface evolves enough in time, the RT surfaces, the length keeps increasing because of the growth of the Einstein-Rosen ridge. And eventually, there's a new saddle, a thermal saddle, in which remains on either side of the black hole and does not cross the Einstein-Rosen ridge, which starts dominating the entanglement entropy formula. And so for this reason, these nice considerations of geometry and even dynamics from information theory quantity don't really apply to those deep interior regions. So in particular, things that are very, very deep inside of the black hole, for example. So our proposed solution is to study other geometric quantities, which can actually reach deeper into the bulk. And famously, when this was proposed, the first few ideas was to observe geometric quantities that are actually related to this Einstein-Rosen ridge that is growing without bound with time. And so the first thing that people considered was just something like the volume of the Einstein-Rosen ridge. And that gave rise to the idea of this complexity equals volume proposal. And then shortly afterwards, this idea of also computing a sort of the action associated to the Einstein-Rosen ridge by computing the action of this so-called Wheeler-DeWitt patch was also proposed. And these quantities actually satisfy some of some things that people expect something like complexity to satisfy. And I will go into that in a second. But before that, I'll just mention that there are various other proposals. For example, shortly after these two initial proposals, complexity V and CA, it came CV 2.0, which basically is complexity equals action. But instead of evaluating the on-shell action on the Wheeler-DeWitt patch, this patch that we're seeing in this diagram over here, one would evaluate the space-time volume. And it would still satisfy the same type of nice properties that one would want these quantities to satisfy. And then much more recently, there's this new story of the complexity equals anything, which proposes many other possible quantities that one could study, which all have some type of geometric interpretation, which also satisfy these important properties. What are these properties that I keep mentioning? Basically, there are things that, because we want to be able to probe the very, very deep interior regions, we would want things that increase for a very long time. But in particular, the ones that have been proposed, they tend to increase linearly, at least in the thermal field double case. And very importantly, they thermalize very, very slowly, which means that they can reach very large values, and therefore they can probe the geometry for much later times, and therefore for much deeper readings. And they also satisfy something called the switchback effect, which won't be too important for what I'll talk today, but it's another property that all these quantities also satisfy. And then, so thinking what type of quantities in information theory one can think of that satisfy all of these properties, the natural thing that people have proposed is something like a state or circuit complexity. So this is, at this level, is still a conjecture, but there have been many qualitative tests that it has passed, and it seems to satisfy a lot of the things that all these other geometric quantities satisfy. So the state complexity, essentially, a way of formulating it is to start with some very, very simple reference state, something that, let's say, doesn't have any entanglement between any of its degrees of freedom. And for a given state, one would choose a set of elementary gates and basically find the circuit or a circuit that maps you from the very simple reference state to whatever target state you have. And then there are many, many different possible circuits. And in particular, the depth or the length of the optimal circuit is what one would define as something like a circuit complexity. Of course, the details of how this would be defined are very model dependent. So there are many different models of complexity for quantum mechanics. But this, in a way, reflects this idea that there are many different geometric quantities that also satisfy the same type of properties. Lastly, I would also mention that one can also consider, given that there is this idea of subregion duality, in which having only a subregion state defined on a particular subregion of a CFT, a holographic CFT, one can reconstruct this entanglement wedge of this holographic dual. There's this idea that the holographic dual of density matrix ends up is actually something like an entanglement wedge. And so one can ask whether it would be possible to define a type of complexity for mixed states as well, or for subregion states. And for the case of holographic complexities, the answer is very simple. You can just restrict the existing holographic complexity proposals to the entanglement wedge. So, for example, for the complexity equals volume picture here on the top right, we would have for some subregion A of the boundary quantum field theory, and given its HRT surface here in the sort of squashed cone shape, what one would do is that we would then find the surface with maximal volume that is anchored at the subregion A and the HRT surface. And then similarly for the complexity equals action, one could do the same thing, in which instead of evaluating the action on the full Wheeler-DeWitt patch, which would continue here, one would take the intersection of the Wheeler-DeWitt patch with the entanglement wedge of that region, and then one would compute the on-shell action instead of on the full Wheeler-DeWitt patch on that restricted section of the Wheeler-DeWitt patch. Okay, so now let's go into one of the main things that I wanted to discuss, and this is to talk about the entanglement entropy and complexity of islands. So to do this, I first have to mention a little bit what islands are, these entanglement islands. And to do this, one of course has to talk about the information paradox. So the information paradox essentially is essentially a tension between the apparent endless increase of entanglement entropy of radiation, or equivalently of the black hole, as it evaporates, and the aforementioned limit in the thermodynamic of the entanglement entropy that has to be upper bounded by the thermodynamic entropy of in any quantum theory. The main issue is that while the black hole evaporates, the event horizon keeps shrinking, and so the thermodynamic entropy of that system, namely the area of the event horizon, keeps shrinking. While if one would naively compute the entanglement entropy of the Hawking radiation, because it keeps being produced by Hawking pairs in which one falls into the black hole and the other one leaves, and these Hawking pairs are actually supposed to be entangled, one would naively think that the entanglement entropy keeps increasing without bound. And indeed, the first semi-classical computations that people did famously said this, and it brought to this apparent paradox during black hole evaporation. So just graphically, the idea is that the thermodynamic entropy keeps increasing with time, while the naive estimate for the entanglement entropy of the black hole would keep increasing. So there would be some tension here. And this is resolved by precisely this island rule. The idea is that when dealing with a theory that has dynamical gravity, there are two things that have to be amended. So for one thing, when computing the entropy of a particular subset of degrees of freedom in some region R, instead of simply computing the entanglement entropy of that subregion R, one has to, first of all, add this Bekenstein-Hawking term, which is proportional to the area of that region. Then second of all, one has to allow the possibility of including so-called entanglement islands. The idea is that for some subset of degrees freedom in some region R, you can allow other regions inside of the gravitational region of the theory. And instead of computing the entanglement entropy of only the degrees of freedom inside of R, of the fields inside of R, you can compute the entanglement entropy of R with the island. which if they're very highly entangled, it might reduce the entanglement entropy of R union I compared to the entanglement entropy of R. But one can only do this at the cost of adding an extra Bekenstein-Hawking term, or an extra area term, which is given by the area of the island itself in Planck units. And of course, the area of any region in Planck units is usually very, very big. And so islands are actually only relevant when there's a huge amount of entanglement between R and I. But it turns out that this is exactly what happens when these type of tensions of information paradox occur. It's precisely because there's a lot of entanglement between the region whose entanglement entropy we're trying to compute and somewhere inside of the black hole or inside of your gravitational region. So just to outline a little bit how this resolves the paradox. When gravity is included, we should allow for these entanglement islands. And so what we find, instead of this linear increase of entropy, we find the so-called Page curve, which is as follows. At early times, there's not enough entanglement between the radiation and somewhere inside of the black hole. And so the islands don't really come into play. So one would get this sort of linear increase in entanglement entropy because there's more and more Hawking radiation being captured by, let's say, the bath or falling into the black hole. However, if we also take into account the possible saddles where there's islands, the Hawking pairs of each of the radiation are actually being accumulated somewhere inside of the black hole. And in particular, when the pair has left and we count it as radiation, but we also have an island and it falls into the island, that entanglement entropy doesn't really contribute to the total entanglement entropy of the region R union island. And so what ends up happening is that the entanglement entropy of the total region starts decreasing as the area of the event horizon decreases. So eventually, at late enough times, there's enough entanglement between what one would call the radiation and the inside of the black hole that including this island would actually give you less generalized entropy. And that's precisely when the stage transition occurs and when one gets into an island transition, into an island phase, excuse me. Okay, so these islands they were motivated by this information paradox, and they were shown through sort of gravitational path integrals for lower dimensional gravity theories. But I want to focus now on a type of model called the easy island models, in which these type of transitions, the island transitions, actually come out from just regular holographic entanglement entropy transitions that are already very well known. So this it consists of a doubly holographic model in which we use a Randall-Sundrum beam rule model. So the idea is that one would start with some higher dimensional ADS-D+1, let's say some region, and then one would excise exactly half of the asymptotic boundary by putting instead an end of the world brane with some tension. So one would have this action, a bulk action, which is in this example just an Einstein-Hilbert action in the bulk, and then some tension on the brane. And then taking two copies of this exact same setup, one identifies the two at the brane. So this would be this little image on the right side. Then the Israel junction conditions would actually locate the brane. So the brane would dynamically set its own profile. And it turns out that for a constant tension, they end up taking these lower dimensional ADS slices. So they are ADS-D slices of ADS-D+1. So what does this mean? So just to recap what I just described, this is what ends up happening is that these models have two layers of holography because there's going to be some induced gravity on the brane, which itself is also a lower dimensional anti-de Sitter geometry. So to quickly explain how this works, the bulk, there are three perspectives because they are each related by a layer of holography. The bulk perspective is the one that I just described. There are two asymptotically ADS-D+1 theories with a codimension 1 brane with some tension, and they're identified. So that would be sort of like the picture in A. Then by using the Randall-Sundrum mechanism and the holographic dual of the bulk gravity, we can sort of reinterpret the dynamical gravity in this ADS-D+1 as instead being some holographic CFT on the boundary on a sphere, plus a Randall-Sundrum gravity induced on the brane, which is on a gravitational brane, is anchored at the hemisphere, plus the same holographic CFT on the brane. So that would be the sort of image that we have here in the middle. And then they mentioned, because we have an anti-de Sitter D gravity theory, which is some exotic gravity theory with some Randall-Sundrum gravity plus some holographic CFT. But invoking holography once again, one could say that this ADS gravity can also be interpreted as some type of conformal defect on the hemisphere itself. And therefore, we arrive at the boundary perspective, in which we have simply a holographic CFT on a sphere coupled to a conformal defect on its hemisphere. So the nice thing, and the reason these models are called the easy island models, is because when considering the brane perspective, meaning this intermediate perspective in which we have a CFT on a sphere and some exotic gravity theory on the brane, then by considering different configurations of subregions of the CFT, we can actually find island transitions without having to do any type of path integral considerations. It simply comes out of the very well-known transition between connected and disconnected phases of the holographic entanglement entropy. So for example, if we have, once we have this CFT on a circle, if we compute the entanglement entropy of two regions that are some angle, some with a belt away from the conformal defect, by varying the angle of this opening, we can transition between a disconnected region when the region whose entanglement entropy, so R, is small enough, we would be in disconnected region, but when that region is bigger, one would induce this transition into a connected phase. And of course, if you consider the entanglement wedge in the connected phase, importantly, it includes part of the gravitational region, because remember that this blue line over here in the brane perspective is part of our theory, where we have this dynamical gravity, this sort of exotic dynamical gravity living on the brane. So to explain a little bit how these things can be done and computed, it all relies on using this Pfefferman-Graham expansion. It relies on this ambient metric construction, in which we sort of decompose the metric away from some particular place. Usually it's the asymptotic boundary, but what we will do here is that we will do the same Pfefferman-Graham expansion, but instead of on a normal asymptotic boundary, it's on the asymptotic boundary that has been excised. So in doing so, this is already well known, but this transverse metric can actually be expanded term by term in terms of the boundary metric. So this boundary metric would be the metric that would be at the asymptotic boundary that we have actually removed by instead putting this end of the world brane. So for example, the first term in this asymptotic expansion corresponds simply to the shooting tensor of the boundary metric. If we cared about much higher order terms, then the expectation value of the stress sensor would also contribute into this asymptotic expansion. But for the things that I will be explaining now, it's not really necessary. Now, taking this Pfefferman-Graham expansion and plugging it back into the bulk action and further integrating out the z direction, we can actually find this effective action. This is actually what the Randall-Sundrum mechanism how it works. Integrating out this degrees of freedom basically induces a gravitational action on the brane. This is some higher curvature gravity that gets induced on the brane. We have a leading order, something that looks exactly like the Amsterdam-Hubble action, with some effective cosmological with some effective length scale. This length scale can actually be tuned by tuning the tension of the brane. Okay, so by making the tension approach some critical value, the length scale can become either very large or very small. And then we have some gravitational couplings here, which are written in terms of the bulk G Newton. Okay. Now, This, as I mentioned before, this theory and this gravitational theory is actually a non-local theory. What happens is that when doing this trick of integrating out this higher dimensional local gravity action, what one gets is a non-local action on the brane. But it's a non-local action that comes as a series in L squared times the Ricci scalar, which, because our branes are just ADS-D, they are actually just a power in the ratio of the two ADS length scales, the bulk ADS length scale and the effective ADS length scale of the brane. And of course, the two can also be written in terms of this coordinate ZB, which is essentially something like the distance between the location of the world brane and the asymptotic boundary, which was excised by it. And in particular, if we take the brane to be very close to the asymptotic boundary, which of course can be done by tuning the tension of our brane, we can actually make it so that the higher order terms are much, much smaller relative comparative to the leading terms. And so we have a quasi-local theory. So a theory in which the locality is set by this very small parameter. And so we call this natural expansion parameter. I'll be calling it the localization parameter for this reason. It, roughly speaking, works as a type of UV cutoff for a theory, where in reality, what it means is that for any length scales below that length scale, the theory doesn't really look local. It looks like some non-local mess. And lastly, let me mention that one can also add an intrinsic gravitational action to the brane and redo everything that I just explained. Instead of having only the tension on the brane, we can also modify the tension and then add some intrinsic Einstein-Hilbert action, for example, on the brane. And then doing the same process actually gives the exact same result. So we get the same induced action, but now, importantly, the coupling of the Einstein-Hilbert term, so this the effective, is different from the coupling of the higher curvature terms. And it differs by a factor of 1 over d brane, where that's the G Newton of the induced gravitational action. Maybe it's clear if I just show here. So the effective is the one that multiplies the normal Einstein-Hilbert terms, and the Randolph-Summon one is the one that multiplies all the higher order terms. Okay, and then let me just mention that for d equals 2, the I effective is actually strictly non-local. There's no Einstein-Hilbert action that gets induced. Instead, it looks like R log R, and this is roughly speaking like an on-shell Polyakov action. Furthermore, we cannot, an Einstein-Hilbert action would be topological for d equals 2. So instead of adding a type of Einstein-Hilbert action on the brane, what one can do is add a JT gravity action on the brane. Now for the main message that I want to give by studying this model is to try to interpret the entanglement entropy and the complexity in the island phase using this toy model as a way of actually computing what the leading order terms would be. So the idea is simply to, okay, so first of all, we are interested in the entanglement of islands and complexity of islands. So we're going to be restricting ourselves to the connected phase in which there is an island. And it is to use the exact same trick of using the Pfefferman-Graham expansion, but also of the embedding of the whatever surface you're trying to maximize. So in this example, we're trying to extremize the area of this codimension 2 surface, capital sigma R. So what we do is that we do an Pfefferman-Graham expansion of the embedding of sigma R in our geometry. And very nicely, the leading term, the leading correction to the embedding, it's also given by just some geometric quantities evaluated in whichever region you are interested. So for example, here, if we're doing the Pfefferman-Graham expansion close to what would be the asymptotic boundary, which is very close to the brane, what we get is an expansion in terms of Z over L of the actual position of the HRT surface. So expanding this around the brane and plugging this back into the entanglement entropy formula, together with the Pfefferman-Graham expansion of the metric and whatnot, we can actually find leading contributions of the entanglement entropy. in the island phase. So there are these universal UV contributions, which are related to the fact that our HRT surface is going to all the way to the asymptotic boundary. And this is sort of universal. It always happens whenever you have a holographic CFT. And then after that, there are the next biggest terms when localization parameter is really small. It's essentially the area of the quantum extremal surface, this little sigma r, which is the intersection of the HRT surface with the brane. And the reason this is very large is because it's going to be A over the appropriate power of this very small localization parameter. It works in the same way as the UV cutoff works for the UV contributions of this entanglement entropy. We can also keep going and keep looking at the next subleading order terms. And what's very nice is that the leading contribution of the entanglement entropy ends up being the Waldung entropy of the induced gravitational action. So this exotic Randall-Sundrum gravitational action, if we compute the Waldung entropy, that's exactly the term that would appear as a leading order contribution of the entanglement entropy due to the fact that there is an island. So it provides a pretty nice interpretation of this leading contribution. Is simply the fact that we have now included, even though we're computing the entanglement entropy of our region R, because our region R somehow contains information of the island itself, then the entanglement entropy across the boundary of the island itself is going to give us the subleading order contribution of the entanglement entropy. So since the HRT surface extremizes the entanglement entropy, then it follows that the profile of the quantum extremal surface, so this intersection of HRT surface and the brane, is actually one that extremizes the Waldung entropy. And what I was mentioning here is that we can see that there's the usual UV structure of entanglement entropy, which is associated to the UV entanglement across the boundary of R, and that's the leading order term. And then the subleading one would come from the fact that we also have some entanglement between the gravitational regions that are not on the island and that are in the island. So there's not UV entanglement, but there's order ZV over L entanglement. So it's entanglement at the level of the locality of the theory on the brane. Okay, so now moving on to complexity. We can do the exact same story, but now with complexity. It's basically the same idea, the same computations, but now in one higher dimension. And for what we did was for complexity equals volume. In theory, it would be possible to do it for other complexity proposals, but there are more subtleties, and this is why we focus on the complexity equals volume. So the idea is once again to apply the Fermi expansion and to put it back into the complexity equals volume formula. And in doing so, we can find once again that there are some universal UV. There's some universal UV contribution, which comes from the UV entanglement of the region R, excuse me, on the whole region, not just across the boundary. And then the subleading order contribution ends up being something like the volume of the island itself. Where once again, this is going to be like the volume over the localization length, to the appropriate power. Another thing one can do is that the UV divergence is actually canceled when considering a so-called mutual complexity, so that one could actually get rid of these, and the mutual complexity would actually just, the leading order term of the mutual complexity would actually be precisely the complexity of the island, sorry, the volume of the island. Okay, so then doing this to the next subleading order term, what one would get is a so-called generalized volume. So this is some quantity, sort of similar to the Waldung entropy for entropy, which one can define from the induced gravity action as a proposed generalization of volume. And similarly to the entanglement story, because the island, because the codimension one surface B maximizes the volume, it follows that the profile of the island, so the intersection of it with the brane, maximizes this generalized volume. And similar to before, there's this UV contribution the complexity, which is just given by the generalized volume of the region itself. And this is due to the UV entanglement structure in R itself. And then the subleading term would be given by the generalized volume of the island itself. And in particular, it is actually the complexity. The holographic complexity is actually discontinuous as opposed to entanglement entropy. And that increase is at leading order, just the complexity of the island that is now contained inside of the entanglement wedge of R. And yeah, okay. So, and this discontinuity is actually very generic. I'll mention that in a little bit, actually towards the end. I think for the sake of time, I'm going to just very quickly say that this is just to show the shape of the generalized volume, and it has a similar structure as a Waldung entropy. It has a so-called Wald term, which one can derive from variations of the effective action with respect to the Riemann tensor, and just contracting it with the induced metric and normal wectors. And then there's a so-called Dong correction, which is the one that has the extrinsic curvature terms. So in the Wald term, there's only intrinsic curvature terms, whereas in the Dong correction, there's extrinsic curvature terms. And these type of things were already, well, specifically the ones without the extrinsic curvature terms were already considered previously in the literature, while trying to argue for first law of causal diamonds for higher curvature gravities. So the idea was that one can relate just variations of modular Hamiltonians to things like variations of areas and volumes by keeping, so this is for normal gravity, but then for higher derivative gravity, instead of keeping areas and volumes fixed, one would keep the Wald entropy instead of the area, and some generalized volume, which does not have extrinsic curvature corrections. And it would be interesting to see if a similar thing can be done by considering the extrinsic curvature terms, so that the Wald-Dong entropy has to be kept, is one of the terms that has to be varied, and the other one would be some generalized volume with extrinsic curvature corrections. And it would be interesting to see whether this new generalized volume would correspond to the same one that we computed through these other considerations. Okay, so we can also add an intrinsic gravitational term to the brane action. And to do this, we also need to amend the complexity equals volume term by adding a contact term on the brane. The idea is that because there is a dynamical gravity on the brane and intrinsic gravity on the brane, one should also add an extra contribution to the complexity equals volume. And in doing so, we actually derive the exact same result that we did without the intrinsic gravity, where once again, the effective is the same as one, as it also gets corrected by 1 over G brane, as mentioned before. And the story is the same for entanglement entropy. Entanglement entropy, the entanglement entropy proposal also needs to be amended by a contact term. And the last thing that we did in this, that I'll mention about this project is that we can also double check this. So this was all sort of first done with an Einstein-Hilbert action in the bulk to see what a proposal for a generalized volume would be. And then to check whether this is something that actually seems consistent, we can also propose a generalized complexity equals volume for a higher derivative gravity, in which instead of asking to maximize the volume, we ask to maximize this generalized volume functional. And in doing so, we can actually compute the same things. And so, for example, we started with a bulk gravity action, which is not just Einstein-Hilbert, but also with a Gauss-Bonnet term, or with an FR in general, with an FR gravity. And the same arguments follow, and the same structure sort of emerges, that the leading order in this generalized complexity equals volume is going to be a UV contribution just due to the entanglement of their subregion R, but then the subleading term would be the generalized volume of the island itself. Okay, so now let's move on to the sort of second part of the talk. And for this one, I want to emphasize how some bounds on entanglement and complexity can actually provide some bounds on the type of gravities that can be allowed in these brane world models. To do this, we need bounds on entanglement and complexity. And there's an actually proved bound for entanglement for something called entanglement velocity. Entanglement velocity is a normalized rate of entanglement growth, which is really useful for systems that have uniform energy density. So imagine some microstate that has some uniform energy density, defining this quantity, which is the change in the entanglement entropy of some region, divided by the area of that region, and the entanglement entropy of a thermal state with the same energy density as whatever microstate you're interested in. It turns out that this entanglement velocity is actually upper bounded in 2-dimensional CFTs. In higher dimensional CFTs, this actually hasn't been proven. There's only like late time bounds. There are no bounds that are satisfied at all times. So what we will do is that we will focus on PD CFTs, so ADS3 CFT2s. And in particular, if we take a region that's very large, this upper bound tells us that the entanglement velocity is upper bounded by 1. A similar bound is often considered in complexity, and this one was derived by Lloyd, and which was trying to consider what would be the speed of computation of a so-called ultimate laptop. And just using sort of physical bounds on things like the speed of light and uncertainty principles, he was able to derive how quickly the most optimal computer would be able to produce logical operations. And basically, he found that the energy is what bounds the number of operations that can be done. In particular, the operations per second are upper bounded by twice the energy over pi h bar. And so considering any physical system as a sort of computer and any change in the physical system as a type of operation, this can also be argued to be an upper bound on complexity growth. So in particular, the rate of change of complexity has to be upper bounded by the energy. And in particular, this certain holographic complexity proposals actually saturate this bound. And this actually gives another sort of view on something that has been said many times in the literature, this idea of black holes as being some sort of ultimate computers, where people have considered this from different points of view, like fast scrambling or thermalization and other considerations. And this is another way in which this idea of black holes as being ultra fast computers arises. Okay, so the model that I would like to use these bounds in are these black hole plus end of the world branes. So these are single-sided black hole microstate geometries, which consist of can be built from starting with a double-sided planar black hole, for example, and one can cap off one of the sides by an end of the world brane. And these type of states are often considered as black hole microstates with some type of semi-classical geometry. The idea is that we have this, this is written in higher dimensions, but I'll restrict in the next slide to 2 dimensions. The idea is that we have some double-sided black hole, and then we add an end of the world brane. So it's going to be inside of the black hole. And so there's only one side of there's only one asymptotic boundary. And so it's a state of a single copy of the CFT instead of something like a thermal field double. There's a nice and Hilbert action, there's some counter terms, and this is the terms that are added on the brane, which has some tension. Now, the neutral junction conditions determine the location of the brane. So if the brane is subcritical, it will simply go from inside of the black hole, leave as time evolves, go to some maximal value, and then fall back into the black hole. And then there are some other possibilities, like a critical, which doesn't quite fall back in, and a supercritical, which reaches the left asymptotic boundary. But for the purposes of what I'll be discussing, we will only care about the subcritical case. And I will note that in addition, one can add a JT gravity action on the brane. So here I'm specifically restricting to ADS3 CFT2, precisely because I will want to use these entanglement velocity bounds on the CFT. The idea is that the type of intrinsic gravity actions that one can add would be things like JT gravity or some other dilaton term. But to be precise, we'll talk about JT gravity. Okay, so if we have some JT action on the brane, the location of the brane is then determined by a cosmological constant, sort of like this, where maybe I didn't say it here, but these are global coordinates where y goes from minus pi over 2 to pi over 2, and tau goes from minus pi over 2 to tau over 2, to pi over 2. Okay, and then the Dileton profile can also be found by varying the metric on the brane. So it's given by this very nice formula, where phi naught is actually constrained by the parameters that we have already described, things like the tension of the brane and the cosmological constant. But phi 1 is a constant that in principle is free. So this is what people usually call the JT coupling. But as we'll show shortly, there are actually bounds on the type of JT couplings, or the values of the JT couplings, that are due to known entanglement and complexity growth bounds. So let's review quickly how this can be done via entanglement entropy. The idea is to consider some interval of the CFT that is large enough at a given time, such that the connected HRT surface is still the one that dominates in the entanglement entropy. So when considering the entanglement entropy of some region A, there are two competing saddles, and the thermal saddle is time independent, but the connected saddle actually keeps increasing with time because it crosses the Einstein-Rosen bridge. So eventually it will thermalize. But here we are considering a time, or rather intervals that are large enough such that at whatever time we have decided, we pick an interval large enough that the connected surface is still the one that dominates. And as mentioned before, when computing the entanglement entropy, we need to include a contact term due to the intrinsic gravity action that we have on the brane. And in this case, it's simply the dileton evaluated at the intersection of the HRT surface and the brane. Okay, so we know what the dileton profile is. So of course, that's actually going to bound, it's going to modify the value of the entanglement entropy. And imposing the upper bound on entanglement velocity, we can find some bounds on the JT coupling. Particularly, there's this JT coupling, which is I've rescaled so that it's dimensionless. And it can be bound by two ways. Either the growth of the entanglement entropy is too fast, so it violates the entanglement velocity bound, or there's actually a discontinuous jump in entanglement, which is an even worse violation of this bound. By the way that this discontinuous jump can occur is because in ADS3, there are no true singularities. And what one considers future and past singularities are simply portals to future and past universes, essentially. And there are for some values of the JT couplings, there are some RT surfaces that can go from one universe to a past universe or to a future universe. For example, here for alpha equals 1, we can see on the left side the RT surfaces that one would normally consider, but then there are these new RT surfaces on the right which go to the past. And it turns out that they actually have lower length. So they would actually give a lower amount of entanglement entropy until eventually they are no longer there. And so that would give us a discontinuous jump in the entanglement entropy. So the first bound that one can derive ends up looking quite simple. It looks like this, where I'll remind you that the position of the brane is actually related to the cosmological constant on the brane. And then the second bound is actually a stronger bound because y is always going to be negative. And it looks like this. It takes this nice closed form. Furthermore, this was already shown in a previous work by my collaborator and some of his collaborators. The entanglement velocity asymptotes to its upper bound. So you can show that the entanglement entropy as a function of time ends up looking like something like this. It goes to 1, where there is some coefficient kappa 1, where if the bounds are satisfied, it is actually strictly positive, so that it is asymptoting from below, and it never violates this entanglement velocity bound. Now, what we're working on currently is that we're doing a similar thing for a complexity bound. So it is that there's this Lloyd bound, and doing a similar computation where now, once again, the complexity equals volume has to have a contact term. We would like to see how the growth rate of complexity bounds the possible JT couplings. So just a quick mention about tuning the Lloyd bound. We actually tune Lloyd bound because the definition of holographic complexity is actually ambiguous. one could always rescale it, and it satisfies all the properties that people talked about. But this is universal late time growth, independent of what tension or cosmological constant or even JT coupling one puts to the brain. The final value of the growth of complexity is actually the same. It is the same as the growth of complexity in the thermal field double. This is because it's associated to the growth of the Einstein-Rosen bridge, which is a universal feature. And so the fact that it's proportional to the mass or the energy, which is similar to the Lloyd bound, and also built from intuition of black holes as being ultimate computers, and also from the fact that the entanglement velocity reaches its maximal value, we propose that late time value is actually also the Lloyd bound. So tuning the complexity equals volume to that normalization, it turns out that the complexity surface falls into the so if we were to project the complexity surface past the end of the world brane, it would fall into the singularity precisely when the Lloyd bound is going to be violated. And anyway, so computing the rate growth of complexity, we can actually find some upper bounds on the JT couplings that are allowed. And once again, we call that the Y brane. It's actually related to the cosmological constant in the brain. And so to recap, there are three possible bounds that one can find from information theoretic constraints on types of JT couplings on the brain in this type of settings. And there are these three, and I plotted this here so that one can see. So the idea is that the magnitude of the JT coupling has to be lower than the lowest of these figures. So we can see that the complexity one actually bounds for certain values of the cosmological constant. And then when the cosmological constant is small enough, it's actually instead the entanglement entropy upbound that should bound the value of the JT coupling. Okay, so just a closing comment, let me mention that what I was doing was focus on some very specific models, but some of the things that I described, one should expect to be true in more general models. So for example, the things that I discussed about entanglement entropy and complexity of islands are actually always going to be true as long as we have a model that has double holography, but also because the results sort of make sense intuitively in the sense that entanglement entropy is the well-known entropy of the theory based on the locality, as well as the complexity is given by the complexity of the island. It would make sense to conjecture that this might be true for other models. The issue about this is that we lack the tools to actually compute these things and prove that it is still the case. I mentioned about the discontinuity in subregion complexity. It's actually very, very general in holography because of there are these transitions in the entanglement computations in which essentially the entanglement wedge is discontinuous, and because all these subregion complexities are associated to the entanglement wedge, there's a sort of universal discontinuity in the subregion complexity or the holographic subregion complexities as we go across these phase transitions. And then lastly, for the entanglement complexity bounds, let me mention that there are currently no strict bounds on entanglement entropy in higher dimensions, but that would be an interesting thing to try to compute. Instead, there are late time bounds, and so it would be interesting to try to apply these type of bounds. And also whether these apply to other brain world models. They should, it's just that the computations might not be quite as clean. Yeah, just because I'm sort of out of time, I'll just do this here. Thank you for listening.
Yeah, thank you very much for your nice talk. So I've got a few questions, but maybe other people want to go ahead. So let me, Sergio, please.
Okay, yeah, thanks for the nice talk, Juan. So let me see. I think that you mentioned at some point that there were some subtleties if you wanted to do this construction for, these observations about the complexity in the easy island picture for other type of observables that have been getting more popular with it with time. So is it just like from the technical point of view, or do you mean that there might be some other subtleties about like a more conceptual?
I think it's mostly technical.
Okay.
Although I do think that there's a question about whether the Wheeler-DeWitt patch, when you have an island, should be emanated from light. So to do the Wheeler-DeWitt patch, you start with your boundary region, and you shoot some null rays. When you're in an island phase, there's also some island region that is sort of separated from that, and maybe it's trivial to say that the Wheeler-DeWitt patch should also have some null rays going from there, but I'm not entirely sure. I think that's something that's the only thing that I think is a conceptual question, but the others would be mostly technical.
Okay.
Like that you have to put all these counter terms, and it's a more complicated.
I guess you can generalize it to the NET proposal, right? For the codimension 0.
I think that's another question will arise there. Yeah.
Right. Okay. How about for instance, you have to include like this generalized volume, and that when you include like intrinsic gravity on the brane, like that also modifies this volume proposal that you were mentioning. Like, have you thought about how that can be used in, let's say, if you had the action proposal or some other type of proposal?
Yeah. Okay, that's true. That's another. That's another issue. That's not just a technical question. I'm not sure exactly how the complexity equals action should be modified. Whether there should be a counter term or a contact term rather.
Yeah.
I think. I don't know. I would have to think about it carefully. I don't think I can answer on the spot.
Yeah. I guess you can ask something similar also in this other picture about the last point that you were making to make the bounds. Sorry, to compare with the Lloyd bound, that you will also need to like have some type of modification if you use a different type of proposal in that case.
Yeah. By the way, the complexity equals action was when it was first defined. The coefficient was precisely one such that the growth rate of complexity of the thermal field double would saturate the Lloyd bound. So that one is already, even though the definition that is in the literature already satisfies this saturation. The complexity volume is not, and that I think is because it was before they started considering the Lloyd bound when it was first defined.
Okay. Yeah, thanks.
Further questions? So let me ask a follow-up question to Sergio's one. So you said that you expect that the complexity should be discontinuous if you also involve the island. But do you have a rough idea why this should be true, or for like C being anything? So for such proposals, why it should be always discontinuous?
Yeah, so I think this discontinuity is strictly speaking for the subregion complexities. So the complexities themselves have to be continuous. And in fact, the Lloyd bound is something that tells you that it has to be complex. It has to be continuous, because at discontinuity would violate this Lloyd bound. But subregion complexities don't have this Lloyd bound. But okay, so the point is that these for any holographic complexity, if we're prescribing these holographic complexities as the intersection of any holographic complexity that you want with the entanglement wedge, the discontinuity itself comes from the fact that the entanglement wedge is discontinuous. So you go from, see if I can see a picture. Oh. You go from something that looks like this in the middle, something that looks like that on the right. And so there's this huge region of the entanglement wedge that suddenly appears. So it seems like there is actually something discontinuous occurring at the level of the state. And any sort of geometric quantity that you want to intersect with the entanglement wedge, I expect would also have a type of continuity across those transitions.
Okay, thanks. So are there further questions? So that seems to be not the case. Then let's start recording. Maybe then a few other questions will pop out.